Welcome to lecture 5 on properties of triangles. In today's class, we will be discussing the ortho center of a triangle and the associated pedal triangle. So, let us see what we mean by the ortho center of a triangle ABC. So, let us say that we have this triangle ABC, which I am drawing right now. So, let us say this is A, this is vertex B and this is vertex C. And then we draw perpendiculars from each of these vertices to the opposite side. So, we drop a perpendicular from A to the side BC. So, let that perpendicular be this straight line, therefore, this is 90 degrees. And let this perpendicular intersect or meet this side BC at a point D. And similarly, we draw another perpendicular from B to the opposite side AC. So, this is 90 degrees. And we call this point where BE, which is the line perpendicular to AC. So, the point on the line AC where the perpendicular from B meets the line AC, we denote it by the point E. So, this point of intersection of both these perpendiculars, which I denote by the point O. So, this point is what is called the ortho center, and we will in fact show that if you join O and C with a straight line, and if we produce this straight line further. So, the straight line CO when produced further is going to meet the side AB of the triangle at, let us say, a point F, and we will show that even this angle AFC is equal to 90 degrees. So, that essentially also means that CF is the perpendicular from the vertex C to the opposite side AB. So, essentially then what we have is that all these three perpendiculars intersect at a common point O, and this point O is called the ortho center of triangle ABC. So, this is the ortho center of the triangle ABC. Of course, here we have taken an example of a acute, almost acute angle triangle, and that is why for this case we see that the ortho center lies inside the triangle, but that is not a must. There are many examples of triangles where the ortho center might lie outside the triangle, and it is not very difficult to construct such examples. But then for this triangle ABC, we will have to prove that this straight line CO when produced to F is such that the angle AFC is 90 degree. So, essentially this straight line CF is perpendicular to the side AB of the triangle ABC. So, how do we prove this? So, of course, to start with, let us denote this angle here by alpha, And then if we look at these two triangles BDO and AOE. So, if we look at both these triangles, then of course, this angle is equal to this angle, and then this angle is also the same as this angle, which is also 90 degree, and therefore, this angle must be equal to this angle. Therefore, this angle also has to be alpha. Then of course, because this entire angle is equal to B, this angle has to be B minus alpha. Similarly, because this entire angle is A, this angle has to be A minus alpha. And then it is not very difficult to see that. And then the next thing is that if we look at the triangle AOB. So, if we look at this triangle AOB, then it is very easy to find out this angle, because the sum of these three angles has to be 180 degrees, and therefore, from there it is easy to see that this particular angle is equal to 180 minus A minus alpha plus B minus alpha, which will be equal to 2 alpha plus 180 minus A plus B. But we know that A plus B plus C is already 180 degrees, and therefore, this entire thing is actually equal to 2 alpha plus C. So, this particular angle here is C plus 2 alpha, and therefore, this angle is also C plus 2 alpha. And then let us look at the, if we look at the quadrilateral CDOE. So, if we look at the quadrilateral CDOE, we know that the sum of all the internal angles of a quadrilateral is equal to 360 degrees, and therefore, so this is angle C, therefore, C plus pi by 2 plus, and this is C plus 2 alpha plus, and this is of course pi by 2, has to be equal to 2 pi. And from there, what that implies, what this equation implies is that C plus alpha is equal to pi over 2, and therefore, this angle alpha is nothing but equal to pi by 2 minus C. So, this angle alpha is pi by 2 minus C, but this triangle BOD, so this triangle BOD is a right angle triangle, and therefore, this angle must be equal to C, because C plus pi by 2 minus C, because alpha is pi by 2 minus C. So, C plus pi by 2 minus C plus pi by 2 is equal to pi, which is 180 degrees. And then using this information, remember that ultimately what we have to show is that this angle AFC is equal to 90 degrees. So, that is what we have to show ultimately, and in order to show that, let us first, because if we see this triangle FBC, so let us look at this triangle FBC. So, this angle is known to us, it is B. Now, if we can find this little angle, let us say gamma, then we should be able to find this angle, or rather this angle AFC, which we want to show that it is 90 degree, will be equal to simply the sum of gamma and this angle B. But let us look at this. So, the length of this side is equal to C, this entire side is B, and this side is A. Now, if you look at the right angle triangle ABD, then this length is obviously equal to C times cosine of this angle B. So, it is C times cosine of B. And similarly, this length over here is, so this is B. So, B times cosine of this angle is C. So, B times cosine of C. If we look at the triangle, the right angle triangle BOD, then in the right angle triangle, so in the right angle triangle BOD, what we have is that tan of C, so tan of this angle C is equal to C cos B over OD, from where it is very easy to see that OD is equal to C cos B over tan C. So, now we have an expression for this length OD, and then if we look at the other right angle triangle, which is CDO. So, if we look at the right angle triangle CDO, then we see that tan of gamma is equal to OD divided by CD. So, and OD is equal to this. So, it is essentially C cos B. So, this is OD divided by CD, which is B cos C, and little simplification gives us that tan of gamma equals C cos B over B sin C. Now, from the sine law, if we remember the sine law, then from the sine law we know that C by sin C is equal to B by sin B. So, we use this relation in this equation, then we can replace this C by sin C, we can replace this ratio by B by sin B, and then this tan gamma will simply be equal to cos of beta divided by sine of beta, which is cot of beta, and we know that cot of beta is equal to, so this tan of gamma, if we use the sine law, if we use this sine law, then we essentially replace this ratio C by sin C, we replace it by B by sin B, and then what we get is that tan gamma is equal to cot of beta, cot of B. So, we get tan gamma is cot of B, which is nothing but tan of pi by 2 minus B, because cot of theta for any angle theta is tan of pi by 2 minus theta. So, ultimately what we get is that tan gamma is equal to tan of pi by 2 minus B, and since both gamma and pi by 2 minus B fall in the interval minus pi by 2 to plus pi by 2, because we have considered an acute angle triangle over here. So, all the angles here, so this angle gamma as well as the angle B are going to be between 0 and pi by 2. So, this gamma is between 0 and pi by 2, and B is also between 0 and pi by 2, and because the tan function is monotonically increasing in the interval 0 to pi by 2, therefore, the fact that tan gamma is equal to tan of pi by 2 minus B, along with the fact that both gamma and pi by 2 minus B lie in the range 0 to 2 pi. So, if we write this nicely, what we have shown so far is that tan of gamma is equal to tan of pi by 2 minus B, and both gamma belongs to 0 to pi by 2 and B also belongs to 0 to pi by 2. And therefore, because the tan function is a monotonically increasing function in this range, it is implied that gamma is nothing but equal to pi by 2 minus b. So, since gamma is equal to pi by 2 minus b, if you look at this triangle FBC, then we know that this is pi by 2 minus b, this is b. So, the sum of this entire angle and this angle is already equal to b plus pi by 2 minus b, which is pi by 2, and therefore, this angle, the remaining third angle of the triangle FBC, has to be pi by 2. So, this has to be pi by 2. So, this essentially finishes the proof of the fact that the straight line CO, when produced further, it intersects the side AB at a point F in such a way that this straight line CF is perpendicular to the side AB. So, this is essentially 90 degrees. So, now we have shown that all these three perpendiculars from a vertex to the opposite side are definitely going to intersect at a common point O, which is called the ortho center of the triangle ABC, and of course, it is a unique point because these three perpendiculars will only intersect at one point. So, next, moving ahead, we would be interested in finding the length of or the distance or the length of the straight line segment. If we go back to the, so next we will be interested in calculating expressions of these distances OD, OE, OF, and also the other distances OB, OA, and OC. So, let us redraw the triangle ABC and the ortho center and the perpendiculars. So, let us say that this is our triangle ABC. So, this is the ortho center O, and what we have shown so far is that, of course, these are all perpendiculars. So, it is not very difficult to, if we just look at the, for example, if you look at the triangle BEC, then this entire angle is C, and therefore, this angle has to be pi by 2 minus C. Similarly, we can show that this angle over here by looking at the triangle FBC, it is very easy to show that this angle is pi by 2 minus B, and this is something that we had already proved in the previous slide. Now, in the triangle BOD, since it is a right angle triangle and this angle is pi by 2 minus C, it follows that this angle has to be C, and therefore, this angle is also C. Similarly, in this triangle DOC, which is also a right angle triangle, because this angle is pi by 2 minus B, it follows that this angle should also be equal to B, and since CF is a straight line, the remaining angle here is A. This of course is B and this is A. Now, let us try to find an expression for OD and OB. So, it is not very difficult because we know that this length BD is nothing but this AB times cos of this angle B, because this triangle ABD is a right angle triangle, and therefore, inside this right angle triangle this hypotenuse is of length c, and this angle is b, and therefore the length of this side BD is c times cos of b, c times cos of b. In the triangle BOD, which is also a right angle triangle, we can write that tan of C is equal to BD divided by OD, and BD is C cos B. So, it is equal to C cos B divided by OD, from where it follows that OD is equal to C cos B divided by tan of C, which is equal to C cos B cos C over sine of C. Now, from the sine law, we know that these ratios C by sine C, B by sine B, and A by sine A are all equal. Also, from our discussion on the circumcenter and the circumcircle, and of course the circumradius, we know that the expression for the circumradius of the triangle ABC is given by R, which is equal to A by 2 sine A, which is also equal to B by 2 sine B. This is also equal to C by 2 sine C. So, this is already known to us, and therefore, here we can replace this ratio C by sine C by 2R, because from this equality it follows that C by sine C is equal to 2 times the circumradius of the triangle ABC. And hence, what we finally get is that OD is equal to, if we use this formula, then it is equal to 2 times the circumradius of the triangle ABC times cos B times cos C. In a similar manner, we can also write the expressions for the lengths OF and OE. It is not very difficult to show that OF is equal to 2R times cos A times cos B, and OE is equal to 2R times cos A times cos C. Now, for these lengths OB, we again have to consider the right angle triangle BOD, and in this right angle triangle BOD, what we see is that that sine of the angle C in this right angle triangle, sine of C is equal to BD divided by OB. So, that is C cos B divided by OB, and that implies that OB is equal to C cos B by sine of C. But from this relation here, we know that C by sine C is already equal to 2R, and therefore, this is equal to 2R into cos of B. In the same manner, it can also be shown that OC is equal to 2R into cos of C, and also that OA is equal to 2R into cos of A. Next, we define something which is known as the Petal triangle of the triangle ABC. So, let us redraw the triangle ABC along with the perpendiculars and the ortho center. So, let us say that this is our triangle ABC with these perpendiculars. Now, these points where the perpendicular intersects with the opposite side are called petals. So, these points D, E and F are petals, and if we join all these petals by straight lines, then we get this triangle FDE. So, this triangle FDE, which is called the pedal triangle of the triangle ABC. So, this triangle FDE is the pedal triangle of triangle ABC. So, next we will try to find expressions for the lengths and the angles of this pedal triangle. Of course, corresponding to any given triangle, there is always a unique pedal triangle, because the location of these pedals are unique. So, to find the expressions for the angles of the internal angles of this pedal triangle, let us start by first trying to compute this angle BFD, which I have denoted by theta. We of course know that this length BD is nothing but C into cos B. Similarly, if we look at the right angle triangle FBC, then BF is equal to this entire length A times cos of this angle B. So, this length is A cos B. And of course, this angle is B itself. And therefore, if we consider this triangle BFD and we apply the sine law to this triangle. So, of course, because this angle is B, it is clear that this angle is nothing but pi minus B plus theta. By applying the sine law, so we apply the sine law to the triangle BFD, and what we end up getting is that C cos B over, so this side BD over the sine of the angle opposite to this side, which is theta. So, this divided by sine theta has to be equal to the length of this side. So, the ratio of the length of this side, which is A cos B, divided by the sine of the angle opposite to this side, which is this angle. So, divided by sine of pi minus B plus theta. But we already know this result, that for any angle x, sine of pi minus x is equal to sine of x, and therefore, this sine of pi minus B plus theta is the same as sine of B plus theta. So, then we get the equality that C cos B over sine theta is equal to A cos B over sine of B plus theta, which implies that sine of B plus theta over sine theta is equal to A upon C. And we then open up this sine B plus theta using the sine A plus B type formula, and what we get is that sine B cos theta plus cos B sine theta divided by sine theta is equal to A by C. And from here we get that sine B into cotangent of theta plus cosine B is equal to A by C. Taking it forward to the next slide, we get sine B cot theta is equal to A by C minus cosine of B. And here we are going to use the cosine formula, from where we know that cos of B is equal to, so cos of B is equal to A square plus C square minus B square over 2AC, and then if we combine these two fractions, we end up getting this entire thing to be equal to A square plus B square minus C square. Again, from the cosine type formula, we know that the cos of angle C, so let us write it here. So we know that cos of C we know is equal to A square plus B square minus C square over 2AB, and therefore from here we get that A square plus square minus C square. So from here we get that A square plus B square minus C square is 2AB times cos of C. So we use this, if we use this expression instead of this in this equation, what we end up getting is that sine B cot theta is equal to 2AB cosine of C over 2AC, which is equal to B cosine of C over C. And then if we take this sine B term to the right hand side, we get cot of theta is equal to B by sine B times cosine of C by C. But we know that from the sine law, we know that B by sine B is the same as C by sine C. So this is equal to C by sine C times cosine of C by C, which is equal to cot of C. So ultimately what we get is that cot of theta is the same as cot of C, and because both theta as well as C, both of them belong to the interval 0 to pi, and therefore from there it is very easy to conclude that theta must be equal to C. So if we go back to our picture that we had, what we see is that, so in this picture what we have shown is that this angle theta is actually equal to the angle C. So this is, so instead of theta, what we have here is theta equal to C, and therefore let's replace this theta by the angle C. And therefore, because this is C, it obviously follows that, because if you remember, this angle BFC is equal to 90 degrees, and therefore this little angle over here has to be, so this little angle over here is pi by 2 minus C. Similarly, we can also show in just a similar manner what we have done here. we can also show that angle AFE, which is this angle, is also equal to c degrees. So, we can show that this angle AFE is also c, and because AFC is 90 degrees, it follows that this angle is also equal to, so this angle is also equal to pi by 2 minus c. Now, because this angle is B, this is C, it follows that this angle is equal to A, and then using the same style of proof, it is not very difficult to show that this angle is also A. And therefore, what follows is that because this angle ADC and ADB are both 90 degrees, it follows that these two angles are also equal, and they are equal to the value pi by 2 minus A. So, essentially what we are seeing here is that and of course, for this remaining third angle here also what we can show is that because this is entire angle is C, this is A, that is why this has to be equal to B. Similarly, because this entire angle is A and this is C, it follows that this angle also has to be B. So, this is also B, and since this is 90 degrees, it again follows that these two angles are again equal, and their value is pi by 2 minus B. So, the angle BED, so BED is equal to the angle BEF, and that is equal to pi by 2 minus B. So, now if we look at this figure here, we have the exact expression for all the angles, for all the internal angles of this pedal triangle FDE. So, the internal angles are, so this angle over here is simply equal to pi minus 2c, this angle is pi minus 2b, and this angle is pi minus 2a. So, the angles are, the three angles are pi minus 2a, pi minus 2b, and pi minus 2c. There is another interesting observation here that some of you might have observed, and which is that this particular straight line FC is an angle bisector of this angle of the pedal triangle. So, if you look at this angle EFD of the pedal triangle EFD, so if we look at this angle, then we see that the straight line FC is basically bisecting this angle, because both this little angle here and this little angle here are both equal to pi by 2 minus c. So, this is an angular bisector for the angle EFD. Similarly, AD happens to be the angular bisector of the angle FDE, and also EB, this straight line EB is the perpendicular. So, the straight line EB is the angular bisector of the angle DEF of the pedal triangle. So, eventually what we see is that all these three perpendiculars of the original triangle ABC turn out to be the angular bisector of the three angles of the pedal triangle FED. So, as far as the pedal triangle is concerned, these three angular bisectors meet at a common point O, and therefore, this common point O happens to be the in center or the center of the in circle of the pedal triangle EFD. So, what we have therefore shown is that the ortho center of triangle ABC is the incenter of the pedal triangle of triangle ABC. So, this is a very interesting result which we have just shown, and that happens only because all these three perpendicular bisectors happen to be the angular bisectors of the pedal triangle, and of course, they meet at the ortho center. So, with that we have found the measure of all the angles of the pedal triangle. Next, we would also like to find some expression for the lengths of the sides of the pedal triangle. So, let us again draw the original triangle ABC. So, let us say this is our triangle ABC, and so these are the perpendiculars. And they meet at the ortho center O, which is this point. And when we join the pedals, so these three points D, E and F are called pedals. So, by joining the 3 points, the 3 pedals by straight line, we get the pedal triangle FDE, whose angles we have already computed the expressions for, and we are now interested in expressions for the lengths of the 3 sides of the pedal triangle FED. So, for that we already know, and we have already shown in the previous slide, that this angle is equal to C, this angle is A, and of course, this angle is B. And we already know that this side BD, the length is nothing but C times cos of B, and the length of this side BF is nothing but A times cos of B. And then it is not very difficult to find the length of this side. We just have to use the cosine law on this angle B of the triangle BDF. So, in the triangle BDF, if we apply the cosine law, then what we get is that cos of B, which is this angle, is equal to the squared length of this side plus the squared length of this side minus the squared length of this side. So, C cos B whole square plus, so this is A cos B whole square, then minus this length df, so df whole square divided by 2 times C cos B into A cos B. So, 2 times this side times this side times A cos B and then if we further simplify that, what we get is that cos of B is equal to C square plus A square minus df by cos B whole square divided by 2AC. So, So, for this of course, we have to take cos b square outside as a common term, and that gets cancelled with the cos b square in the denominator. But if you look at the original triangle ABC, then in the original triangle ABC we know that cos of b is equal to c square plus a square minus b square over 2ac. So, if we simply compare these two, then we easily get that this side df of the petal triangle is equal to b times cos b. In a similar manner, it can also be shown that the other two sides are, so the side DE has a length equal to c times cos of c, and this remaining side EF has a length equal to a times cos of a. So, therefore, let us summarize the lengths of the sides and the angles of the petal triangle in through this figure. So, this is the ortho center, these are the three perpendiculars, and by joining the petals DE and F, we end up getting the petal triangle, which I have drawn in blue. And just now what we showed was that so this particular angle here is pi minus 2c, this angle is pi minus 2b, and this angle is pi minus 2a. This length is b cos b, this length is c cos c, and this length is a cos a. So, the lengths have been drawn in the lengths have been written in the green and the angles are in blue. So, this is what we have shown so far, and it is also then, since now we know the measures of all the angles of the petal triangle, and we also know the lengths of the sides, it is not very difficult to find an expression for the area of the petal triangle. So, the area of the petal triangle, which we let us say denote by delta prime, is equal to, and for that so for the area let us consider a perpendicular. So, let us now focus only inside the petal triangle, and let us drop a perpendicular from this vertex E to the side FD. So, let this be the perpendicular, let this be the perpendicular. So, therefore, the area delta prime will be given by half times this base. So, half times b cos b times this the length of this perpendicular in the green dotted line, but this perpendicular in the green dotted line is nothing but, so let us say that this point is K. So, this triangle KEF is a right angle triangle, and therefore, this length KE, so this will be this times KE, but the length KE will be equal to the hypotenuse length, which is A cos A times the sine of the angle, sine of this angle. This angle is pi minus 2c. So, K E will be equal to A cos A into sine of 2c, and therefore, if we put this expression here, what we get is that the area delta prime is equal to B cos B over 2 times K E, but K E is this A cos A sine 2c which can be further simplified to A B over 2 times sine 2c into. So, now we can write this cos A. So, we multiply both the numerator and denominator here by sine A. So, we get sine A cos A over sine A, similarly times sine B cos B over sine B. So, this is cos A, this is cos B. So, cos A cos B, A B over 2 is here and sine 2c is here. This can be written as A by sine A. So, we already have a half here. So, A by sine A. So, we bring this sine A as a denominator to this A over here times B by sine B times sine 2c, but this thing in the numerator here is sine 2A over 2 and this is sine 2B over 2. So, now we move these 2's inside these two terms here. So, that this becomes equal to half into A by 2 sine A times B by 2 sine B times sine 2c into sine 2A into sine 2B. But we already know from previous lectures that both these terms are nothing but equal to the circumradius of this triangle ABC, which is R, and therefore, finally what we have is that the area delta prime of the petal triangle of the triangle ABC is given by R times R is R square. So, R square over 2 times sine 2A sine 2B times sine 2C. So, the area of the petal triangle is given by R square over 2 times the product of the sine of double the angles of the triangle ABC. So, with that we come to an end to this lecture. So, in the next lecture we will continue with deriving expressions for the value of the circumradius and the inradius of the petal triangle, and thereafter we will start discussing what we mean by centroid of a triangle and related properties and also relations between centroid and orthocenter. Thank you.